find out where a data point went in wrong or something? You guys with me? Because that's the worst part, is being human and putting the wrong number in. Okay, I like it. That's the worst part, is being human. It sucks. Okay, all right. So, any more questions on that? Because we're going to move on. Yes.
So, when you ask to compare, you would just say that the correlation is strong to Virginia.
Oh, you would just say it's really close. Like we just said, the prediction was really close to what happened in reality.
And then D, you would say no because there's other factors?
Yeah, there's other factors. So the funny thing about the answer for part D is, I don't know. You can't say no, it won't. You can't say yes, it will. All you can say is, I don't know. It's a different kind of test you could run to see if there's a causal relationship, if there's a cause and effect relationship. That's not what this test does. Poor little dude. Okay, maybe. All right. So, what we're going to do today, now that we reviewed that stuff, there's, all right. So the history of this, let me ask you this. Is that the kind of example I've got? Let me see. God, I took the two best examples. No, I didn't. Oh, yes, I did. All right. Let's say that we want to test to see if a die. We want to test to see if a die is weighted. What would it mean if a die, like a one die from a pair of dice? What would it mean if it was weighted? What would happen?
Over 50%.
How often should one show up on a die?
50%.
No.
No,
How many sides on a die? 6. So 1/6. So roughly 17%. 16.666. Everybody with me so far? You with me? I know what you're thinking, but there's more sides. Yeah, I'm like, your die is interesting. So how could I test to see if a die was weighted to have less 1s show up, to have more 6s show up or something, right? So you got all these die hidden on your person, so when you play Yahtzee, you're like, oh yeah, I got the 6 die.
Over that percent.
Think about it. Yeah, okay, I'm with you. So it kind of makes sense that one way to look at it is just to roll a die a bunch of times and see if it happens to be. Now if I roll the die 100 times, is it impossible to not get a single 1? Think about it. If I roll a die 100 times,
Yeah.
could I get nothing but 2s, 3s, 4s, 5s, and 6s? Is it possible? Are you guys alright? You guys?
Yeah.
Alright. You're like, dude, I'm here. Just accept that. I'm like, alright, I can do that. So think about it. That's possible, of course, right? In fact, it's possible to roll nothing but 5s with a normal die. Is it likely? No. I'm not gonna force you to do every step of this, but I'm gonna focus on the two most important parts. So we gotta do a test of a claim. If I claim that this die is weighted somehow so that the results come out different from what I expect, I'm gonna have to do a certain kind of test on it. And it's gotta be more specific, because again, in this case, how many outcomes are there? 6 outcomes, right? So it's kind of hard to track. We don't have any tests so far. Every test we've done is comparing like 2 things at most. So we have to develop we have to use something new. And this new thing is kind of nifty. Well, one thing is it's called a chi-square. Chi looks like an X. It's a Greek letter. Right? It's nothing to do with Dragon Ball. Chi-square distribution So we have z-score distribution, t-score distribution. Now we have chi-square. So I've got another chart for us. Fantastic, Jeff. I was hoping, praying. This thing is so nifty, but obviously we don't have much time to talk about it, which is why I'm going to do the most important use of it. It's called the goodness of fit test. That is the actual name. Goodness of fit. So if I have a die, I'm going to roll a die. Let's say 100 times. Well, let's say something better. I'm going to say 180 times. Why is that better? You guys know, I don't freaking know. How many ones would you expect to show up now?
1/6.
Say it again. You got it?
1/6 of 180.
1/6 of 180. How often would a 1 show up on average? 1 out of every 6 times. Right? Now we know it doesn't have to, but that's what we expect. And the kick-ass thing about that is we actually call it expected. So let me make sure I got which way did I want to set this up? That makes sense. Okay, got it. So we got 1, 2, 3, 4, 5, 6. Observed, expected. So observed, expected. Let's fill in that expected part. So each number should show up how many times on average?
17%.
Roughly. 1/6. What's 1/6 of 180? Now you see why I picked 180. 30. So each number I expect there to be 31s, 32s, 33, 34, 35, 36s. Shit, Joe. Let's line them up. All right, that's rough. Can somebody tell me what kind of distribution that is? If you drew a histogram, what would it look like? What would it look like? How tall would the bars be? They'd all go up to 30. So that would be what kind of distribution? Uniform, kick ass. So if we ever believe that something is uniformly distributed across all the possible options, you just divide the total by how many options there are, because they should all get the same amount. Okay, maybe. So that's what you guys can fill in. I've got to tell you this. So let's say we roll that die, and let's say we get 19 ones. What you got, Jeff? 34 twos, 33 threes. What do you got? You got to keep track of it somehow. I know, man. Oh, okay, 32, 31, 10. Oh, and then 31. All right, I like it. All right. I'm going to stay on myself. Come on, Jeff, you can do it. Let me stop for a second. The expected you fill in based on what I expect to happen. If I think they're going to be uniformly distributed, then I can just fill it in all with the same number based on how many total there was. The observed, I got to tell you what somebody observed. And that's how you fill that in. Okay, I like it. Now, what makes immediate sense? What should the next column be? I know you've got to look at it on the paper, but why does it make sense? How do I tell if this is close to being uniformly distributed? Well, why can we see that maybe it isn't?
Because they're not equal.
They're not equal. But again, so let me ask you this. Let me remind you about this. Okay. If I roll a die 100 times, will I get 30 of anything necessarily? I could, but do I have to? Does that mean the die is freaky somehow? Just like in a hypothesis test, when I do a sample, not only does my result have to be different in some direction, it's got to be different enough. So none of them are exactly 30, right? But most of them are close to 30, but one of them is way the shit off. Okay. So why does it make sense? And the next thing to do is take the difference of those and square it. Because the difference is exactly at the heart of this whole thing. How different is what I saw from what I expected to see? Right, that part should make immediate sense, right? I know what I expect to see, and I know what I saw, and if I'm doing a test about did it do what I thought it should, I should take a difference between those two things. And why did we square it? The same reason we squared when we did standard deviation before. So that the negative shit isn't negative anymore. Oh, there it is. So you guys can help me out here. So this will be, this will be 11 squared. These won't be too easy, too hard. What's 11 squared? You guys see that? 11 squared. 121. Everybody with me? So this will be 4 squared, 16. 3 squared, 2 squared, 1 squared, 1 squared. Kick ass. So that is a measure of the square differences between what I expected to see and what I actually saw. How's everybody doing? Some of you guys are looking at me like, what is 19 minus 30? Negative 11 squared, 121. 34 minus 30, 4 squared, 16. So remember when we had to square the stuff for standard deviation because when they're negative and they add them all up, it goes to zero. It's like bullshit. So I got to square it just to get rid of that crap. That's one reason why we don't take square roots because it is a chi-square distribution. Let me stop for a second. I know you're always worried about where we're going, but what we have done, does it make some sort of sense with the idea of what we're trying to see? Is this die doing what I think it should do? That seems to make sense as to what somebody would do. This next step, let's see if it makes sense. This next step is, I want to get a relative difference. 121 seems like a big difference, but how is it related to what I expected? So when I divide by E, I'm getting a relative difference. This is the part that might come out gross. 121 divided by 30 is like 4.03, I think.
Yep.
Kick ass. 3. Yeah, but you see what I'm doing? Observed minus expected squared divided by 30. That's sort of like dividing by the total to make a relative frequency. It's a relative difference. Relatively, how important is the difference? So if you had $5 more than me, and I got $1, you're like in a much better situation. You can afford lunch somewhere, right? And I can't. If you got $5 more than me and I got $1 million, do I give a shit? No. So that relative difference, $5 is not $5. It depends on how much we're talking about. In this case, about 30. Keep going. What's 16 divided by 30? 0.5. 5? 3? Okay. And then 9 divided by 30? 0.3. That's a nice one. 4 divided by 30? 0.13? Being very trusting. 1 divided by 30 is 0.0333333. All right. Yes?
Do we always leave these to 2 decimals?
Oh, yeah, that's fine. I mean, you can imagine we're going to be doing this in the calculator, list 1, list 2, list 3. That's a really smart. You don't have to, but I sure as all hell would, right? All right, now, the chi-squared formula for this situation is just the sum of these. That's the chi-square formula. It's sort of like the z-score formula. Not in what it looks like, but in what it does. We're going to compare it to a number on the chart to see if there's enough evidence. So let's just see what that is, and then I got to come and bring the theory in. I wanted to start with something concrete, and then I got to bring some theory in. I always got to, you know me. So when you add all this stuff up, what do you get?
5.05.
Sounds about right. 5.05. Okay. So here's the theory, because we don't know what the shit that number means right now. They're not z-scores. They're not. So that does not mean anything by itself yet. So let me ask you this. If these two were exactly the same, what would chi-square come out to be? If these two, the observed and the expected, were exactly the same, what would chi-square come out to be? If O and E were the same, chi-square would come out to be 0, right? Because all the differences would be 0. So 0 would be perfectly lined up. So this is a measure of how far away we are from being perfectly lined up. Right? And again, I got to do this, even though if you hate it, hypothesis says, but Z star was a measure of how far away our sample got. Are you with me? So we basically just got the equivalent of Z star. That's what our sample did. What we need is the number to compare that to, like the rejection region. So here's the crazy thing about this. I'm always trying to balance how much I tell you without leaving too much out, but the neat thing about this, if you took the Z distribution and folded it on itself, multiplying all that you got, you would end up with the chi-square distribution. Freaky, I know. So here's what it looks like. Here's a chi-square distribution. I call it the Jabba the Hutt distribution. Let's see if you guys agree with me. It's probably bad. Is it normal? Hell no. Is it symmetric? No. See how long that tail is? It doesn't look like, No, the Java. It's Java for me, all right. That's the chi-square distribution. This is 0. So there's going to be, so let's just get the theory out there. So everybody, hopefully y'all are kind of cool with that. I mean, that should almost the whole way through should make sense as to, all right, I want to see if this is true, well then this kind of makes sense, why I would do this. What I'm missing is, what's the theoretical value that I want to compare it to? Where's my rejection region? So 0 would mean it's strong evidence that it's fine. There's no evidence that it's not the same. So out here somewhere is going to be the rejection region. Okay, maybe. So we just need a chart to be able to look up what this is. Let's say that alpha is 0.05, the standard one. What would this be? If that's 0.05, this area would be 0.95. I like it. And here's the main thing I think is going to really throw you guys off before I give you this chart. The degrees of freedom for a goodness of fit test are based on the number of categories. So how many categories are there? 6. So the degrees of freedom for this is 5. And we call the number of categories K, just because we didn't want to use C, I guess. Categories. Or we spelled bad. We spelled bad. So degrees of freedom is K minus 1 in general. So in this case, the degrees of freedom is 5. So let me give you this chart. Let's figure out how to read this thing. Well, maybe you can do this. More charts than the last chart. Last chart. So let me see if you guys can find. Can you just take a second to see if you can find the score? Let me see if you guys can read this thing. Do you see how it's set up? Stats people got together and we said, how can we screw students over? Let's make a chart that's area to the right. So what's to the right of that? 105. So what's nice is the test we're doing is it's going to match up directly with alpha. Because a goodness of fit test is always a right tail test. Now there are tests you could do that are two tail tests in chi distributions. And that's why they got this and these. So I know alpha is 0.05. And degrees of freedom is 5. So we get 11.071. You guys see that? And notice how these numbers, this is not like Z or T scores at all, because look how freaking huge these get, right? They're based on the sample size. Okay. So 11.071. Let's put that up here. Point the right way. So 11.071. If we got here, if we did get in here, is that evidence that they are not the same? Because what did 0 mean? 0 means that they are the same. The observed and the expected would be exactly the same. So what would it mean if I got way the shit out here? That would be evidence that they are not the same or different. I like it. Maybe. So did we make it far enough away to say that they are officially different? Yeah. Well, what did we get? 5.05. Did we get enough evidence that this die has been weighted? No. Right? Which is not what you probably expected. I mean, is 19 close to 30? No, but it's not far enough away. Why? Again, same reason with hypothesis tests. The fact that I can see they're different. Why is that not good enough? If I can just see they're different. Well, I think it's $3.70. My sample's $3.69. You're stupid wrong. Why is that silly? If I thought the gas price was $3.70 and it's actually $3.69, that's not far away. What is this all based on? We took a sample. Did we do every rolled toss ever? No. We just took 180 times. So of course there's going to be variations in that. So the variations here aren't big enough to tell me it's something more than just what could happen randomly. That's the whole idea. It wasn't far enough away to show that they're not the same. If you roll the die an infinite number of times, it's like eventually the ones would catch up, maybe. Our test doesn't seem to indicate that they wouldn't. Maybe. So, on the handout, I have one problem that's worked out. See how I say if they're uniformly distributed, for example, right? So why did I put a bunch of 7s in the expected? Because how many total did I have? 42. So I took 1/6 of 42 and got 7. Because in this case, again, it just happens to have 6 categories. There are 6 options. I like it. This kind of thing always goes wrong for me because I can't help but eat them. All right. So in this case, we did not find enough evidence. See the 11.071 because it was exactly the same degrees of freedom and alpha. So look at number 2. How's number 2 different? Several things. How's number 2 different? Do I think they're uniformly distributed? No. In fact, I see theoretically where they should be. 20% of the people should have below a 130 blood cholesterol. So forth. You with me? You with me? So, can you fill in the expected category? How many people do we have? 500. So how do I figure out what goes here? 20% of 500. I love it. So the two options for the kind of goodness of fit test I can give you is they're uniformly distributed. So it'd be like that. They all get the same number. Or I give you percentages. So you got to figure out what would go in each by taking the percentages. And of course, the observed one is easy as shit. What's going to go here? Yeah, I tell you everything. Yeah. So go ahead and try to fill this in. Try to get as far as you can in this problem. If you can't get very far at all, just call me over. We can help each other out too. Anybody did not get the practice final? Well, to get this one, we did 20%. This one, we did 30%. Yeah. Since I expect those percentages to show up.
Wait, how do we expect it?
So, if this is uniformly distributed, you just divide the total by how many categories, because then we'll have to get the same amount. This one, I know what percentage of the total should show up in each.
Oh, this.
So 20% of 500 should show up less than 130.
Okay.
So,
And we leave it in percent.
well, this is going to be a decimal number of things. Yeah. Well done, be careful. 20% of, yes, you're going to get a number here. Oh, 2.2 times up. Make them into decimal on both sides. Of means. So 20% of 500. So you put there 0.2 times 500, you put the results of that. And the rest, Jeff, whatever, the rest. This is 450. To 452, is that what that is? So that would be 48, is that right? Oh, 160 for 70, yeah, okay. So this would be let's see. 0.35 would be 150 plus 25. 15 would be 50 plus 25. Is that right? 2, 3, 4, yeah, okay. That's what I'm getting so far.
Wait, how did we get that?
Get what?
The expected. Because
So how many do you expect? What percentage do you expect to be less than 130? 20% of
we can't see.
500.
Oh, so 0.2
Yep.
times
Of means multiply. I don't know what the hell's happening in high school and below that, but of means multiply. Everybody used to know that. So I'm going to kind of build these in the list just to show you what that would look like if you want to do it that way. Shit. All right. There we go. Oh, you calm down now. I like it. So if you want to do it in the list, I'm going to make L3 L1 minus L2 parentheses squared. I'm just going to do exactly the observed are in L1, the expected are in L2, so I'm just going to make it gather parenthesis L1 minus L2 squared. Of course. Oh, Oh, that's a perfect example. So, what mistake did I make just now? I wish I could say it was on purpose, but it isn't.
It's not on the list.
Yeah, it's not on the list. So you always get this kind of error data type. I'm trying to put an entire list into a single spot. Poor little dude. Let's try this again, Jeff. L1 minus L2 squared. That's observed minus expected squared. That's what I get. Yeah, makes sense. Maybe. Because, for example, this would be 132 minus 100, 32 squared comes out to be 1,024.
L4 would be L3.
Yeah, so L4 would just be L3 divided by the expected L2. So that's the sum, that's the observed minus expected squared divided by the expected. That would be L4.